Okay, so in this first lecture, we look at purely algebraic theory of index. From next week, of course, we'll switch to a functional analytic method. But the point of this purely algebraic presentation is that it's kind of instructive and it's easier to understand, and it captures some of the features, not all, but some of the features of the idea of Fredholm operators, finite rank operators, their relations to each other, and the idea of index in purely algebraic setting. So the setting is just linear algebra. Okay, so so imagine you have an operator T from one vector space to another. So this operator T is called Fredholm. If two conditions are satisfied, if kernel of T and co-kernel of T are both finite dimensional. So co-kernel of T, of course, is y divided by image of T. So that's the idea of Fredholm operator. It has finite dimensional kernel and finite dimensional co-kernel. So when you have a Fredholm operator, then you can define its index. T is Fredholm. Its index is defined by, so the notation is IND for index, so it's called index of T. Sometimes we don't even put a bracket around T. It's called index of T, is a difference of two numbers, dimension of kernel and dimension of co-kernel of T, minus dimension of co-kernel of T. Okay, so obviously for this definition to make sense, both kernel and co-kernel of T has to be finite dimensional so that you can take the difference of the dimensions. I should make one remark that this concept is interesting only if both X and Y, these linear spaces X and Y, are infinite dimensional. So just a remark here is that so Fredholm operators are interesting only if X and Y are both infinite dimensional. So in fact, you can easily prove for yourself that if X is finite dimensional and Y is infinite dimensional, and in that situation, there is no Fredholm operator from X to Y. No Fredholm. Similarly, for Y and X, X is infinite dimensional and y is finite dimensional. Okay. So if both are finite dimensional, then again, this concept is not interesting for the following reason. First of all, in that case, any operator is Fredholm from finite dimensional space to finite dimensional, right? In that case, and not only that, the index also is it's not that interesting, although it's relatively interesting, but it's not that interesting because this is independent of t in that case. And index of t turns out to be, well, you can just use rank plus nullity theorem. It turns out to be just dimension of x. So it's just independent of the operator t itself. Okay, so Fredholm operators and index theory is a purely infinite dimensional theory. So it's really interesting only if both x and y are infinite dimensional. So that's something we have to keep in mind. Okay, so there is now a kind of, so what is an example of this? So the simplest example of Fredholm operator, of course, are invertible operators, right? So if t from x to y is invertible, is an isomorphism, then in this case, of course, t is Fredholm. Well, I mean, kernel of t is 0, and t is surjective. Co-kernel of t is also 0, and its index is 0 minus 0, which is 0. So just say index of t is equal to 0. So invertible operators are certainly Fredholm. And one of the ideas of this whole Fredholm theory is that indeed Fredholm operators are kind of almost invertible operators. That's how we should think of Fredholm operators. So Fredholm, so the philosophy, I mean, is that means almost invertible. I mean, this needs some explanation, some experience, some working, but gradually we will develop that idea. Almost invertible. Whatever almost means. Okay. So to understand this idea of what almost means, we have to look at the extreme opposite of the idea of Fredholmness. And that is the idea of finite rank operators. So that's something that's, of course, very well known. So I just say, in this situation, T is finite rank if it is finite rank, right? If dimension of image of T is less than infinite, so has a finite dimension of image, this operator T. So of course, in the case that x and y are both infinite dimensional, that as we discussed is the only interesting case, the finite rank operator is never Fredholm, right? Because it's finite dimensional, so its co-kernel is going to be infinite dimensional. So dimension of y infinite implies that T is not Fredholm. So in a sense, well, I mean, exactly, the two classes are completely disjoint from each other, and they have no intersection. Okay, so so now some properties of finite rank operators I can formulate, and they are very easy to prove. So one lemma is that these finite rank operators inside algebra operators actually form a two-sided idea. So inside L of xx. So L of xx is the set of all linear operators from x to x, and these are finite rank operators from x to x. It's a two-sided idea. It's very easy. In fact, it's easy to see that the sum of two finite rank operators is finite rank. And if you pre-multiply or post-multiply a finite rank operator with any operator, you're going to get finite rank. This is very easy because of properties of linear maps. So this is basic stuff. So, but it's very important to realize that this is a two-sided idea in the space of all linear operators. Now, there is a characterization of Fredholm operators in terms of finite rank operators, which is very important. And that actually, to some extent, explains this idea of that Fredholm operators are almost invertible. So this result is called Atkinson's theorem. So I'm going to recall. Again, this is a purely algebraic analog of a function analytic Atkinson's theorem that we will prove next week. So let me just again, the proof is not difficult, and it's just linear algebra working with subspaces, finding complementary subspaces and stuff like that. So this theorem, I call it algebraic Atkinson theorem. The result is this: T. So we just look at just to simplify notation and presentation. I'm now going to assume y is equal to x, but results with obvious modifications work in general. But just take t from x to x. So a linear map from x to x is Fredholm. If and only if it is invertible modulo this finite rank operators. So if and only T is invertible modulo finite rank operators. R means finite rank operators. So modulo finite rank operators being invertible, we can write it in two ways. If pi of t belonging to the quotient algebra, L of xx divided by finite rank xx is invertible, where this pi is the natural projection from L of XX. So this is a ring of the, I mean, it's an algebra or your field or whatever. And this is a two-sided ideal. So we can take the quotient and go into the quotient algebra, which is a unital algebra again. So the result says that T is Fredholm here, if and only if you push it into this quotient algebra, becomes an invertible element of this algebra. So of course, now this is equivalent to saying that there exists an operator S, again from X to X, such that ST and TS are not identity, but they are but the difference to 1 is almost 0 in the sense that they are finite rank operators. So ST minus 1 belongs to finite rank, and TS minus 1 also belongs to finite rank XX. So this S obviously is not unique. There could be many such as. This S can be called the quasi-inverse or pseudo-inverse. And in PDE theory, as we will discuss soon, this is called a parametrics for T. So T, so S is called a parametrics or pseudo-inverse, or similar names of T. Again, the proof in both directions, first of all, the proof of equivalence of the two statements is obvious, and the proof of the theorem in one form or the other, it's not difficult. It's, again, just simple linear algebra. But it's an extremely interesting result. And it's very, very useful result. Okay, so we will see that this algebra, a kind of a suitable analytic version of this, where we have to complete this finite rank operator to something called compact operators, is going to be an important algebra. So this is a kind of algebraic analog of Kalkin algebra. So that's, we'll see it soon. Okay, so the corollary of this result is that if you have two Fredholm operators, you multiply them, and you're going to get a Fredholm operator again. So that's kind of very interesting, and actually not kind of an important result, but it follows easily from this characterization. So the corollary is that T1 and T2 Fredholm implies that T1, T2 is again Fredholm. Okay, so that's good. So this is space of Fredholm operators from, oh, this is finite rank. For Fredholm, I didn't have a notation. Yeah, okay. So the space of Fredholm operators is closed under multiplication. It contains the identity operator, but it's certainly not closed under addition. So it's not a subspace. And it's not a subgroup either, but it's the pullback under this natural projection map of a group, the group of invertible elements here. So that's But now a natural question is, what is the index of T1, T2? So that's an important result. So that gives us the index. So index of T1, T2 is equal to index of T1 plus index of T2. Its proof needs some ideas. Because this is purely algebraic, there is, of course, has to be a purely algebraic proof. It exists, so it uses the following idea. So the idea of proof. So I won't prove it, I just give the idea of proof with some hint. You can work it out yourself. So the idea of proof is this. So imagine you have a chain complex. So imagine this is a chain complex. Co-chain complex in this case has to be called, it doesn't matter. So of course you can take its cohomology. So you get these groups H0, H1, H2, Hn. So this is the cohomology of this chain complex. So maybe I denote this chain complex by V, and this is going to be H of V. So there is a kind of Euler formula in this case, which is or Euler characteristic. So definition, the Euler characteristic of V so maybe I denote it by chi V, is alternating sum of dimensions of these vector spaces. Okay. So of course, for this to make sense, we are assuming that these VIs are all finite dimensional. Right? So that's what we assume. And then these H0, H1, H2s, so on, are also going to be finite dimensional. So we can take the Euler characteristic of cohomology as well. So I of H of B is going to be sum minus 1 to the I dimension of HR. And so the result is that Euler characteristic of V and Euler characteristic of H of B are the same. And you can easily prove it using rank plus nullity theorem from linear algebra, stuff like that. So chi of B is equal to chi of H of B. So in particular, if this complex is acyclic, in the sense that if it doesn't have any homology or cohomology, then if it is exact, in other words, then all these guys are 0, so this right-hand side is going to be 0, so alternating sums of dimensions is 0. So the corollary is that if V is exact, it means H of V equal to 0 for all in all dimensions, and then sum minus 1 to the I dimensional the I is equal to 0. So now you can use this result with the definition of index. And then you can cook up an exact sequence and you can apply this result and you get this multiplicative or addition formula for index. So corollary is that index of T1, T2 is equal to index of T1 plus index of T2. So that's a very, very important formula. It shows that index is it's acting like a log function. Turns multiplication of these operators into index of multiplication is sum of indices. So it's a bit like log. Okay. So now maybe it's time for some examples. So let me, first of all, before moving on, let me give a very simple algebraic example to convince you that index can be actually any integer. There are operators whose index is any integer. So so again, very simple example. Let B equal to C of X. Polynomials in one variable. It doesn't matter if it is over C or any field. It's the same. So this is an infinite dimensional vector space. Let's take T, well, maybe X with my notation. So let's take T from X to X. So this T is multiplication by X operator. So T of F on X is equal to mx of F. So at X is equal to X F of X. Okay. So this is this operator. Okay, so obviously T is injective. So dimension of kernel of T is 0. Now, this T is not surjective because it maps into those polynomials that have a factor of X. In other words, it's mapping into polynomials that basically vanish at 0. So that space has codimension 1 because we can write any polynomial as a constant plus polynomial that has an X term. So, and dimension of co-kernel of T is equal to 1. So both are finite, so T is Fredholm. And index of T is equal to -1. Now you can iterate this T, say n times. Well, you see, Tn is multiplication by x to the power n. If you iterate it n times, you're multiplying by x to the power n. So the same thing, again, this T is injective, but its co-kernel is going to be n, so it's going to be -n. Now this, of course, we could have used this result to obtain this -n formula, but independently also we can. So all negative numbers are obtainable as index of some operators, very simple operators, but very, very important operator, by the way. And what about positive numbers? So instead of multiplying by x, we can differentiate, for example. That's another operator. So, so consider this operator tfx is equal to f prime of x for any polynomial. Now, this operator obviously is not injective because constant, the derivative of constant function is 0, right? But that's the kernel. So kernel of t in this case is just constant function. So dimension of kernel is 1. But this operator is definitely surjective because you can write any polynomial as the derivative of another polynomial by taking antiderivative, which is going to be a polynomial, and then take derivative of the antiderivative. So, and t is surjective. So dimension of co-kernel is 0. So we get indeed the index of t is equal to 1. Now, like in this case, you can iterate this process n times. And once you do that, you're going to get an operator whose index is n, but n is a non-negative integer. So Tn f x is equal to the nth derivative of f x. Obviously, kernel of Tn is just polynomials of degree at most n minus 1, right? So this is C1, dx sum Cx, dx sum Cx n minus 1. So dimension of kernel is equal to n. But again, because this t is surjective, so Tn is also surjective. In any case, so dimension of co-kernel of t is also 0, so index of Tn, rather. So index of Tn is n in this case. So this again verifies or confirms the formula for the multiplication, because we have this operator raised to power n, so its index is index of t plus index of t plus index of t n times, which is 1 plus 1 plus 1. Now, these two operators, differentiation and multiplication operators, have a kind of closely related operators, which are called unilateral shift operators. Now, we can have forward shift and backward shift. So maybe I mentioned these things because they play an important role later on. They're good examples, anyhow. So these examples are purely algebraic. This needs Hyperspace, but that's a very simple theory, in fact. So let x equal to L2, which is the set of all sequences A0, A1, so on, such that they are square integrable. I mean, square summable. Okay, so now the operator t can be defined t of a and to be a n minus 1. Or, yeah. So this operator now, so let me just think about it like this. So let's look at backward shift. So this is the operator that sends A0, A1, so on. So push it backward one step. So this is going to be equal to A1, A0. So now you can see that this operator, or A0, A2, A1, A2, I'm sorry. You can see that A0 always goes to 0. So, but then otherwise, so the kernel of T basically here is really just things that exist in the first coordinate. So dimension of kernel of T is equal to 1, but T is surjective. Any L2 sequence, you can start from 0, for example, and then get this L2 sequence as a result of backward shift. So this operator, then index of this is equal to 1. Now you can also look at the maybe we can also look at forward shift. So in this case, T of A0, A1, so on, is equal to 0, A0, A1. Now this operator is obviously injective. So this then kernel of T is 0. So its dimension of kernel of T is 0. But then in this case, dimension of co-kernel is going to be 1. Okay. So of course, then the index is going to be -1. Okay, so these two examples are rather similar. So we can, so but the thing is, this is in the context of Hilbert space, because L2 is a Hilbert space, and this operator T, in this case, forward shift, backward shift, are actually bounded operators. They're very important operators, in fact. And they are Fredholm now. We just checked that they are Fredholm. And the iterations are also Fredholm. Okay. So one more result that is going to be very, very important for us is the stability of index under perturbations. So in this purely algebraic case, the result is a stability of index under perturbations by finite rank operators. So that's an important result. So stability. finite rank perturbations. So the relevant theorem is this. If T is Fredholm and T0 is a finite rank operator, then T plus T0 is Fredholm and its index is the same. And not only it's Fredholm, so finite rank perturbations of Fredholm is Fredholm, and the index doesn't change. So it's kind of small changes in some sense to T does not change its Fredholm nature and does not change its index. Again, this is not very difficult and can be done purely algebraically. So we are going to prove these results in analytic context, so I'm not going to bother with the proof in this case. But it's good to keep in mind. So the results that we looked in this case were perturbation invariance of Fredholm operators, their index, basic examples of shift operators, forward, backward shift, and the addition formula for index, and Atkinson's theorem, and those results. Okay, so now one example. So I give this example only just to kind of motivate what's going to come next. Even if you're interested in proving some operators are Fredholm in this context, because this is a purely algebraic context. We have some cases where we want to prove some operators are Fredholm, but the proof is actually quite hard if you don't use analysis. So the analysis could be useful even when you want to prove some operators that make sense in purely algebraic context to be Fredholm. So what I mean is this. So let's look at one very, very important class of operators. This is not pure algebra, but it can be explained algebraically. And this is the class of Toeplitz operators. So let's look at this now. So Toeplitz operators. So let's start with the case of Hyperspace H equal to L2 of S1. The L2 2-pi periodic functions, or just L2 functions on the circle where you put the standard measure on S1, which is the Haar measure on S1. So this has an important subspace, the Hardy space. So this is the Hardy space. So this is defined as those L2 functions whose Fourier coefficients in negative direction are all vanish. Do vanish, right? So this is, so let f hat of n by definition be equal to 1 over 2 pi integral f of x e to the I n x minus I n x, and then I go from 0 to 2 pi dx. So these are the Fourier coefficients. So of course, under this Fourier transform, I mean this Fourier series stuff, we have this correspondence between L2 of S. We have an isometry between L2 of S and L2 of Z. So L2 of Z are all L2 sequences that are indexed by integers, all integers, positive or negative. Such that some absolute value of an squared is less than infinity, and from minus infinity to plus infinity. So L2 square, L2 sum sequences like that. So the isomorphism of these two Hilbert spaces, this is one aspect of Plancherel formula. I mean, one of the first basic results of Fourier theory is that you send this function f, L2 function, to its Fourier coefficients, f hat n. In fact, basic Fourier theory tells you that, Fourier series theory tells you that, indeed, integral, so norm of x squared, which is 1 over 2 pi 0 to 2 pi absolute value of f of x squared dx, is equal to sum of Fourier coefficients squared. So this is, in this case, is the Plancherel formula, and this is the Hilbert space linear isomorphism between this Hilbert space and that. So now, what is Hardy space? So the Hardy space is the space of all those functions whose negative Fourier coefficients vanish. So F, so it's a definition maybe. F belongs to H2, and only if the negative Fourier coefficient of F is equal to 0 for n less than 0. So it consists of those functions that in Fourier modes, they exist only in the positive direction. In the negative direction, they are 0. So, okay. So now let's let P from L2 of S1 to H2. So this is the projection operator, right? Projection operator. Into this subspace. So this just cuts down the negative part and takes the positive part only. So P of AN in this picture is just A0, A1, A2 belongs to L2, which is H2, of course. So that's the projection operator. Now, what is Toeplitz operator? So what we can do the following. Now, for any f, say belonging to continuous functions on the circle, although it can be done in a more general setting, but let's just look at continuous functions. So define the Toeplitz operator with symbol F. So this operator TF, it's an operator that it goes from the hardest space to hardest space again. It goes from H2 to H2. It's defined like this. You multiply by F, and then you project again, because when you multiply by F, you may go out of, easily go out of the hardest space, and then, but you want to come back to the hardest space, you have to project. So I can say TF is equal to P MF. So this MF is the multiplication operator by F. So this operator then is just so TF G is equal to P of G for all G belonging to H2. So okay, so this is the kind of first example of hardest space and the Toeplitz operators, but then this can be extended vastly in many directions, and actually it's a very interesting topic. Gives you many interesting examples in higher dimensions, and you can even work over general manifolds, and so we'll discuss that soon, but for now this is good. So now so the following thing is true. So it's the following. This operator TF is Fredholm if and only if F is non-zero or is invertible. TF. So first of all, let me say that F belongs to C of S1, right? So TF is Fredholm if and only if F belongs to C of S1, so it's invertible. So, well, being invertible means that, of course, F of Z is different from 0 for all Z belonging to S1. So that's, so proving this result using, I mean, this is a purely, you can say this is a purely algebraic context because, well, I have this vector space H2, and we are going from H2 to H2. This is the operator in this case. And we want to prove that this is Fredholm, but what we know from the algebraic theory is not enough. So I will prove this as a result of analytic theory that we will develop next. So of course now, there's going to be an index for this. In that case, so in the case that F is invertible, index of TF is equal to minus winding number of F around 0. It's kind of first index theorem in some sense. One of the first, or simplest types of index theorems, if you want. So to prove such results, prove that this is Fredholm, and to prove that the index indeed is going to be given by this, we need more theory than just purely algebraic theory. So this, by the way, is I believe is due to Goldberg and Krein. There is also some attribution to Wiener. These operators in similar forms, sometimes they're called Wiener-Hopf operators. It's not exactly the same, but I think it's related. So Goldberg, Krein, or Wiener index theorem is this result that we want to prove next. So this is the winding number of F around 0. So we'll look at this soon. Okay, so guys have a good day, and we will